Every now and then I like to dip my toes back into the world of physics, having always found myself drawn to it as a means of understanding reality. Frequently, when taking another lap through, I come back with a sense of awe for all that has been figured out and laid in front of us in order to get where we are. I also tend to have a different perspective on reality itself. One moment like this came several years ago after watching a documentary on the history of mathematics, and it centered on the question of, is math an invention or a discovery? Let me tell you, something so simple sent me into a complete tailwind of what could be. From the computers with their logic gates, to music and its connection to math, and so many things between. Much more recently, I had that experience after reading a book by Carlo Rovelli called The Order of Time. The book is a brief encapsulation of what contemporary physics knows about time. How it works, how it bends, and why time gets more complicated the more and more precise that you're measuring it. Right up until this conversation, that book had me curiously pondering how time moves and unfolds, while simultaneously ruining any number of sci-fi concepts as being unfortunately unrealistic. Holding these two things in my mind, when I knew I was going to talk with this episode's guest, I came up with two questions. The first being, is mathematics an invention or a discovery? Where we end up going with that question wasn't at all where I was expecting. Creativity. How creativity expresses itself, and the process folks go through to conjure it, is one I always find fascinating. Because when the act of creativity gets distilled down, it ends up looking really similar, no matter the medium. One medium that I never considered quite in the same manner before this conversation is math. But Einstein would step away from his work in order to play the piano. And often, as his fingers are moving around the keyboard, an idea would come and strike him, which looks very similar to the virtue espoused in taking a walk, like Plato did in his olive grove, Thoreau at Walden Pond, or even Dirac wandering through the countryside. Infamous are those moments of eureka that come when the answer or concept seem to strike down like lightning from the ether. It can be for a new song, a new way to represent reality like Cubism, or Impressionism, or a solution you were searching for. Creativity is the denominator across these few examples, with just a couple ways of sparking it. Whether it's Thomas Edison taking a nap, intentionally setting it up to wake him up in a jolt, or Archimedes sliding into his bath. Usually, though, when we celebrate creativity, it's in the post-production of whatever was built, rarely in the recognition of what's needed. And when it's a need for creativity, which in its essence is a new means of calculation, for most of us that muscle to think in that manner was never cultivated or interesting enough. Math as a system of calculation is distant to most of us, especially higher order math, anything near what physics uses to move objects in space or explain a black hole. We can easily see that adding a donut to a box of 3 donuts means we now have 4 donuts. What's lost to us now, though, is understanding of that as a discovery, how that was an explicit way of describing what was already there, but now known and being able to be calculated. If we want to be a baker, simply counting, being able to understand ratios and fractions will get us about as far as we need to go. But if we want to start to extrapolate past this moment, to chart a path out of an object, set a course across the sea, move a telescope in orbit, we quickly need more sophisticated means of calculation. Therein lies a need for creativity, something that my guest for this episode expresses impeccably. In an attempt to put it succinctly, in which Alex does a way better job of being able to describe it, math started as a discovery, and through creativity emerged multiple inventions. Inventions that power our modern world, from GPS systems, microchips, quantum computers, and even our understanding of time, which is the centering of our second question we talked through. Given how time works, how the passing of time is different on one planet than it is another, let alone the time that passes to go from one to the other, our question then is, could an interstellar civilization exist? When we peer through a telescope, we see into the past, a star as it was when the light set out from it, not as it is now. That makes for some heady ideas of how one can travel from one planet to another, with only a few months passing in their perception, but it can end up being 100 years. How could a government be possible? Could it make it possible? The layers of how time works in relation to gravity is only another wrinkle to this, as the time passing within a planet can vary with another if even instant transmission of information was possible. Before this chat, I didn't think a civilization across stars was really possible. I didn't think they could get past this time delay and how great it could be across a distance. Which is rather silly of me now that I think about it, because the ancient world had nothing but carrier pigeons at best, and how much information could a scroll at the back of a pigeon be, and everything else at the speed of a horse at best. That some limiting factor of the civilization would be the order of time. Now, however, I'm still aware of this limit, but the bounds of what a collective species will have to overcome is no longer something that I think is certainly a rule. Just in the same way that I've been pondering how to think in terms of a millennia, and use that as a means to strive for a better sense of today and now, what if that was the order in which a civilization took to organize themselves? Focusing not just on the needs that has to be done here and now, but how this here and now relates to those beyond the stars. How long it may be before we hear from them and what we have to ponder in the meantime. How that may be possible and what that means for all the fun sci-fi is what we end up getting into. This episode I'm joined by Alex Cruikshank, a software engineer, amateur physicist and mathematician, a hacker, and my personal favorite mad scientist. In this episode, we unpacked those two questions. Is math a discovery or an invention? And can an interstellar civilization exist? This episode, thanks to Alex, is full of great explanations of relativity, how time works, and a whole lot in between. Thank you, Alex, for coming on, and thank you for listening. Wherever this finds you on our big, blue, beautiful planet, I hope you're doing well. Take care. All right, I gotta do that cliche thing before the episode starts. If you like what you're hearing, please follow the show on whatever platform you're hearing it through. And if you would, give us a rating as well, as both of those help keep the show going and get it found. One last thing, if you want to submit a topic for me to cover, throw me a person you want me to interview or talk with, even if you want to talk with me, or you just want to tell me how terrible of a job I did on something, check out bandwidth.productions to visit the site and drop us a note. So much better if there was like a beep leading into it. All right, so thank you for your time. I'm going to ask you one question, then we're going to dive into it. What do you like to do that makes you happy?
Play video games, I guess.
What kind of...
Something like that. Hang out with the kids. Yeah, I've been into simulations lately, kind of like, I don't know, like colony builder simulations. And I don't know, I played Star Wars Outlaws, which was pretty good. I like big sandbox games.
Yeah, sandbox games are the best. Like when I first played GTA, which was the first sandbox game I played, it blew my mind.
Yeah. Yeah, look, the next one's coming out sometime soon, right?
I think so. I think I've also been hearing that for a long time.
Well, for 10 years, yeah. It's like, but I don't know. I thought they said November.
Yeah, I don't play video games anymore. I am thinking about playing Kirby 64 again, though.
Oh, wow.
It's a fun game.
Yeah. I've been thinking about playing Katamari again.
What's that?
Ooh, wow. You could get to play Katamari for the first time. It's a Japanese game where you have a little ball and you roll it and you bump into things, and then whatever you bump into becomes part of the ball, and you keep rolling. But it's kind of like, it gets hard to roll if it's not very symmetric, and the bigger you get, the more you can like actually knock over. But the thing is that it keeps going up in scale and bigger, so you can like start out in a room and end up like swallowing continents. So it's like, and it's a crazy game. It's really fun. Looks really good too.
That sounds like fun. I like those.
Highly recommended. It's also on every system now, I think.
Okay, cool. Yeah, that helps because I don't have any of them. I have like Xbox 360 and PlayStation 2, and like, it's like I have Dreamcast, but I think it might be Dreamcast, but I would
PlayStation 3. Yeah. I have to upgrade.
I also have like a
PlayStation 2 to PlayStation 3.
I also have like a really beast computer that I built below me that it would do anything that I needed it to do. But it's funny. I have like my sister-in-law, she plays computer games, and I told her what's in my computer, and her eyes just like lit up. I'm like, I just do it for data science, though. She's like, why?
Right.
Uh, okay, I want to. I know we're going to talk about math and time. Those are like the two things that I wanted to just like throw out and then see how far we get with it. Um, Actually, let me ask you, which of those would you like to talk about first?
Either one's good. We can talk about math.
All right, let's do that. All right, so I posed this question to you for a while ago, and we haven't actually been able to talk about it because we've been saving it for this, which is math a discovery or an invention?
Yeah, I mean, this is like a really old debate. I mean, like 2000 at least years old. And it's actually the idea is it's a discovery is Platonic. So basically, that was Plato's idea. And there's well, you can really argue for both. So let's start with the Platonic idea that it is a discovery. Um, so I mean, there's really good reason. There's basically an argument for it now, like why it's a discovery, and that's because of Gödel and Wittgenstein and Turing. Basically, Gödel with his incompleteness proof, Wittgenstein with formal logic, and then Turing with his regular expressions, kind of like took the idea of math, basically like what you do when you do math, the kind of like the statements that you make, the proofs, the deductions, and convert it into a number system. And then once it was converted into a number system, you can do proofs on it, and they could prove things like you can't prove the consistency of a system within the system itself, or you can't or well, basically, Turing was able to say there are anything that you can prove mathematically, you can prove in a Turing machine, and there's nothing outside of that. You can't. There's no statements outside of that that make sense. So, but the thing is, because of that formalization, that means that there's like a space of mathematical statements that you can make, proofs, like ideas um, that are just out there. They're kind of defined now by Turing. And so you can say that, well, any statement that you make is actually going to be in that space. So it is, in some ways, it's been thought about before the fact that like a statement like that exists. And so you're just must be just discovering it. So there's kind of like a technical argument for that, but it's I don't think that's very satisfying. And I think if we go back to the Greeks and understand where they were coming from with it, there was like they thought that mathematics before like the 17th century or so was very much it was very much more geometry based, and so there were axioms. But the thing is, these axioms were considered to be universal, and so you would discover an axiom, and then you would deduce from those axioms new math, and everything would kind of come out of that. So it's like it's very natural for the Greeks, who were mostly like drawing circles in the sand, and connecting lines and doing constructive proofs like that, to to be able, to consider it to be a discovery. To say that they're not doing creative things, they're finding these things, and I think at that time it might have been actually more desirable to think about it that way, because it's like you're looking for fundamental truths in a world that probably did. I mean, just really didn't have many. It's like we understand the universe much better now than we did then, and there was much more of a connection between mathematics and physics or natural philosophy back then. So it makes sense that in antiquity that you would think of it more as a discovery, but in the really, I guess the 17th and 18th centuries, and into the 19th centuries, there was like much more of a concern with the foundations of mathematics, which required a kind of reformalization of mathematics. Basically, like we, one thing that became clear is that there were all these axioms, didn't necessarily make sense again. You couldn't just add an axiom and expect the system to remain consistent with all the other
Could you
axioms.
define an axiom real quick
Yeah.
and then keep going?
Oh yeah, an axiom is it's basically the thing you can't prove. It's like you have to start with some notion that you just everyone accepts, and I think like certainly with the Greeks, it was like, or with Euclid and geometry, the idea was these axioms are fundamental because if you build your mathematics on top of them, it's consistent with what we think the universe is, which was, pretty close, but not quite right. We know now. And so you like an axiom is that a line is made up of a set of points, say, or it's like two parallel lines never meet, which is a good example of one that we end up getting rid of at some point. But there's so it's you start off with that, and I think everyone knows that you like always knew that you need to keep these to be a very small set, and then everything else you want to prove from it. So if it's possible to there's a statement and an axiom, but you can actually take two axioms and or three or all of them or whatever and derive the other one from it, you get rid of it. It's not an axiom anymore. It's a theorem. And so all the theorems are built on top of the axioms. But what happened, I think, is really in the 19th century mostly, is that it became clear that mathematics, the way we want to do it, you can't just have like a one size fits all set of axioms. It just doesn't work. Or when I say axioms, I also kind of mean like structures, like number systems and things like that. Basically, the things you start out with and then start proving things on top of them. Just there was just too many mathematical ideas for it all to fit into one idea. And the thing is, like, you could clearly do useful mathematics with the stuff. I mean, a lot of this is really coming from calculus, which had a really poor mathematical foundation when in the 17th and 18th century, but so incredibly useful that it wasn't going away from mathematics. So somehow math had to deal with calculus, which eventually it did. But all this analysis eventually led to the idea that you don't have like a single, you don't have a single axiomatic system. You don't have a single, set of structures. What you do, these don't exist out in the world. There isn't like Euclidean geometry. Euclidean geometry isn't the start of everything. What you need to do is you need to break it down into something that is much more abstract, and then start building up and build up however you want. Basically, in modern mathematics, the mathematicians start by talking about what they want to prove, or what basically they start out with talking about their axiomatic system, and the structures that they're going to use, and they build up from that. But the thing is, all mathematics can be built up in different ways. It's just kind of this understanding that you can just you can start however you want to, and it's whether or not that's good math, it's useful or whatever, is one, can it be used in kind of some kind of practical application, or does it really have some aesthetic qualities? It's like like mathematicians like now kind of like are interested or not interested in certain math because a lot of times because it leads to connections in mathematics fields or different fields of mathematics, or sometimes it just sometimes it's just like people think it's a beautiful proof, or like it seems the math itself is interesting. There's a lot of structure that comes out of it, a lot of interesting results that can come out of it, and so that's people get into it for that, and people go this way or that way. And when you start to look at it like that, I mean, it really starts to look a lot more like a creative field. It's like it's more that the direction that you choose to go in mathematics is creative. And, but you still have to follow all the rules, and, the math has to be true. And I think that's really what we talk about when we talk about math being creative.
That was an epic diatribe.
Sorry.
No, that was epic. All right, I'm going to summarize what I think you just said, which is mathematics has evolved over time. And initially, it was more of a discovery because we as in the collective species of Homo sapiens, were literally drawing circles in the sand and figuring things out like, oh shit, pi is a thing. Or, ways in which to, I mean, even just the conceptual, logical grouping of, I have one thing, I have two things, or I have one thing, I have another thing, now I have two things. Like, that's like, oh, wow, look, that's kind of in a way a discovery in the most primitive cavemanish kind of way. So back then it was more of a discovery, but then it started getting over time more abstract. And through that abstraction, creating systems to define the abstraction, which also led to both more things that you can apply abstract conceptions to be able to derive some type of understanding, which then essentially created the way that I'm thinking about this, almost like a divergence in the field of it's becoming more and more and more inventive. And that inventiveness has led to ways of seeing and visualizing it to be that of, I mean, like you said, creativity, which is, what can I create with it? How can I play with these things? I mean, it also kind of gets into like the mathematical beauty of certain things. Like, what is that? Like object E8, I think is what it is. Where it's like this mathematical construct of a 120 dimensional hyperdimensional object, and how they got to that was purely based off of just drawing things that looked cool. Or like I like Escher a lot, like MC Escher. I really quite dig him. Actually, the for this podcast, the logo of it is an MC Escher drawing of the drawing hands of where the hand is drawing itself into existence. But he did that all with just like funny perspectives on lines, which is funny because him as a person was kind of a shit student. Like that his family was constantly trying to get him to be a better and better student. But then it turns out, mathematicians started looking at his work and saying, oh, this is actually a great way of describing, the circular nature of things. And he sparked all this different stuff. So that's super. I have never heard it put that way, in which, because like I watched this whole documentary, I mean, probably a decade ago, playing with this tug of war between the two. And the whole time it was just saying one camp was saying yes, the other camp was saying no, which was maybe just the storytelling of the program. But that's really an interesting way of putting it. It used to be more of a discovery. It's become more of an invention.
Yeah, I think it's really what people want it to be, and I think you can definitely think about it either way. So I think you're right to say both, but I think some people really want to say, no, we are just like discovering this aspect of reality, which is the mathematics that underlies our universe. And then other people are more like, well, no, I want to go my own way and like want to do these things. And I think they want to be creative. I mean, I think the correlations between mathematicians and musicians are well known. And I think actually music is a great analogy to this, because you think about it, there's like staff has 5 lines, or you double it and whatever. And it's like you have so many instruments and so many notes, and, there's only so many ways to arrange them. So all music can be considered to be a discovery as well as a creation, or instead it's almost like the notions are kind of dual to each other.
I really like that. I had a calculus teacher in high school who got me not to sleep in class by he's like who I slept through like all of high school and especially math, because I was just like, oh, I could do this in like 2 seconds. Like I'm not gonna put much effort towards it. But he was like, is anyone here a musician? And it was like me and somebody else who was like in band or something, I think. Honestly, for the life of me, wish I remember what he did. But he was like, oh, he related something in calculus to the circle of fifths. He's like, oh, do you know the circle of fifths? And like, I knew it, but the other person didn't. And he was explaining, I genuinely don't remember what it was, but I remember that was the first time I was like, oh, wait a second, music's math? Wait, what? How is it math? And to your point about music being a discovery, I'm really into jazz, right? And that is purely a discovery exercise. And there's all these different little I think the Barry Harris is the latest guy who I think it's his name, but he created all these different scales. There's people who've created like chromatic scales, which chromatic just means doesn't follow the set pattern of the musical notation. But what they end up discovering is, oh, if you throw this note in here, which is actually technically a sour note or outside the scale, what it ends up doing is sounding really nice in the way it's related to it. Like key changes. I like key changes a lot. And the reason that those sound so good, if you can play it right, is it sounds similar, but it sounds similar because it's shared. ABC notes are shared between the two, and because of that, it has like a natural flow. Even though on paper it's like, where did you go with this? How does that work?
Yeah, I mean, there's a ton of, and naturally in music, because I mean, it's all these frequencies that are doubling every octave, and kind of notes are chromatic notes are generally like a 1/12th of like a doubling, exponentially. But the thing is, what sounds good is when two notes are actually have a very close to a small fraction multiple. So like a not a fourth, but, if you double it, double it's two clean. That's an octave, and it sounds like the same note. But if you triple it, or it's 1/3 higher, or something like that, it sounds really good. And so like all those combinations of where they are in that doubling is like you basically got this exponential thing going on and a much simpler fraction thing going on, and it kind of like there's a lot of interesting complexity there in how things work.
Yeah, no, totally. Because the way that the Western music scale goes, which was something that comes from the Greeks, going back to the discovery part of it, which ties that back in. Some notes are a half step, or half the distance of one note to the other, and the other ones are full distance. And there's interesting things and just musically, the way that the notes work, it's like you said. So like A to A is a doubling of the tonal structure of the actual harmonics of it, right? So it's like like 5, or to make it, so it's like 212, and then it'd be 428 would be the next one up. It's so interesting of how you could play with that. So like bringing it back to key changes, if you do a key change that's half a step up, even though on, let's just say, on a guitar it's the next fret up, it seems like it would be very close, and that you're moving it not that much, but because of the structure of the way the harmonics work, it ends up sounding like a quite jarring change, as opposed to if you do a full step, which is actually on the guitar, it's much further distance, but because of the way the harmonics work, it actually sounds like you're closer together. So like Mariah Carey, she does that a lot. Well, she'll bring it up one just because in the musical scale, it sounds like you're pushing and almost giving more energy to it, as opposed to just a half step, which like Stevie Wonder like doing, because it kind of shifts you off your game for a second.
Yeah, absolutely. It's like all the harmonics are also on like even number fractions, or what can be thought of that way. And so it's like moving up the note. It actually, the way it interacts with the other note, it either lines up with the harmonics or not. It's it's interesting. It's like there's a lot you can do with just the notes without even worrying about like the tone or anything like that.
Yeah, exactly. Which goes back to the whole, I mean, this also is like Einstein, which is such a belabored way of saying it, like everything's relative. Because I mean, one of the big things in jazz is it's not what you're playing, it's what you're playing connected to what you're playing next. So, sometimes they'll hit a high note on the key to kind of throw you off your game, but then once it keeps going, all of a sudden it sounds like it's all woven back in again. Which I wonder if there's some type of analog with mathematics. I'm not astute enough on math.
Yeah, unfortunately, I'm not really as much of a student of music to really be able to comment too much on that. I know a little music theory, but not much.
Yeah, I know. It's like how I am with math. It's like I know enough about math to be dangerous and have some really esoteric thoughts in my head, but not enough to actually do it. Where music theory, I actually especially in the past couple of years, have gotten a little bit more into that.
That's cool.
Yeah, it is. It's also interesting how many people, like for example, like Jimi Hendrix, he came to all of his understanding just by playing around and not at all knowing the theory. Or like what was Green Day? Someone was breaking down a Green Day song, and they're like, "Oh, right now they're doing this. They don't know they're doing this, but this is this complicated thing that they're doing."
Yeah. Yeah, actually, last night or a couple of nights ago, there was a talk about computer shaders for computer graphics, and we were working on functions. People were kind of like trying to build their own shaders, and it's like I've been doing a lot this for a long time, especially the math part. I understand the math a lot, but the thing is, to do that kind of work, you don't actually to do something interesting. You don't have to understand the math. You can just try putting a function in there, or just try wrapping the thing in a function. I mean, a lot of times, even though I do kind of understand the math, it's easier to work that way and just like have just a ton of happy accidents, make it, just like, okay, now this is doing something and it's kind of boring. And then let's try to break it by doing something that I don't even know what's going to happen when you do it. And so there's that kind of mode of just like, yeah, just fooling around and making things happen, which sounds kind of analogous to what you're talking about.
Yeah, no, definitely. I mean, that's a lot of what like Schrodinger and all those quantum guys and early like evolutions of Einstein. That's all that they were doing. What they were exactly doing, I have no idea. I have no way of conceptualizing how they did math like that.
Yeah, there's an anecdote I just learned the other day, which is Einstein and his general relativity, when it's right around the time his paper came out in 1915, he came up with the equations, but they were essentially differential equations. So they described what the solutions would look like, but he didn't have a solution to them. And he said, well, this is going to be tough. It's like, I don't know if anyone's ever going to figure out a solution to this. It's like, or, it's going to take a lot of effort and a lot of mathematicians working on it. It took a month. Schwarzschild come up with a solution in his hospital bed 1 month later.
So interesting. So bringing this back is, I think what we're landing is that it's both. It just depends on how you're applying it.
Yeah. I mean, I think I like the creativity idea. I think there is a creative aspect to it, but it has more to do with what's the mathematics you pursue rather than, what's the mathematics that could possibly exist. It's like you could imagine like a true discovery phase. But, actually, you can have a computer program and they'll just go and prove things. There are systems out there that will do this and systematically go through things. So you can just kind of brute force mathematics. And that would be definitely pure discovery. But the thing is, I don't think anyone thinks that just setting it off to prove everything it possibly could, as far as it can get, starting from some point, would end up generating anything interesting. I think everything it generated would end up being completely boring. No one would be interested. So I think it's that creativity that leads to the interesting results, even though those results still have to be kind of discovered along the way.
I'm trying to. That's really a fascinating idea. So if you were to go off purely on just saying go find whatever the hell you can find, it may actually not come back with all that much. But if you're trying to say, oh, I wonder if I could do these things, you might actually along the way discover something and be able to transform it into something else. That's a really interesting way of putting it.
Yeah, and I think the computer would come up with billions of results, and just none of them would be classified as interesting. They'd all be true, but they just they wouldn't lead to anything or be applicable to any other situation, and so no one would pay any attention.
Huh. Makes me think of string theory, except for people are paying attention.
Yeah. I've been reading a little bit about string theory too, and it's kind of it's sad because yeah, it doesn't seem like there's going to be any way to really resolve anything about it anytime soon. But also, it is really kind of the only game in town. It's like there's not a lot of good unification alternatives out there.
Yeah, I
Loop
mean,
quantum gravity, kind of, but it's like I don't know. There's just so many results in string theory at this point that it's a little hard to like translate those into something else.
yeah, string theory seems to me to just constantly be, oh, let's add another fundamental particle and then it all works. Oh, wait, we got to add another fundamental particle and it all works. It just keeps going that way. Uh, Roger Penrose seems like he's trying that like twister theory, which I haven't even dove into, but he's the only other person
Mm-hmm.
that I think that should be taken seriously that seems to be doing something that's not a little whack-a-mole.
There's a few competing theories out there. I like loop quantum gravity as one, but it's yeah, I don't know. The thing is, everything at this point is hard to test, so there's not going to be a whole lot of like great resolution until there are better experiments or better techniques for getting I don't know, for figuring some of this stuff out.
Let's Okay, that's a perfect segue into talking about how gravity makes an interstellar civilization impossible. Okay, so Carlo Rovelli, awesome physicist. I think loop quantum gravity is actually his
Mm-hmm.
field.
Yep.
Also, he's just a beautiful author. It frustrates me how good he is at writing, and it's the second. It's not even his. Yeah, like I'm reading a translated version into English, and it's writing is not his primary focus, and it's so gorgeous that it frustrates me how good he is. Anyways, his book, I think it's called The Order of Time. So, all right, so he explains how gravity works, and it totally wrecked the idea of ever having like a Star Trek or a Star Wars world in my mind. Because, okay, from my understanding of how gravity and time are essentially the same thing, is we perceive the passing of time here on Earth, and that
Mm-hmm.
has to do with the gravitational forces of Earth and the sun, which is kind of the two major polarities of what's happening here, which create what the passing of time is for us. The passing of time for
It,
somebody. Oh,
they affect the passing of time
okay.
in a very minute way, and so it's something like something not influenced by gravity is going to like experience like Earth gravity is going to experience time differently, but it's a pretty small effect.
Right. Okay. That's a good distinction. Um, which is also like the small effect of like the time passes on top of a table differently than below the table. Like on top of the table,
Mm-hmm.
it passes slightly faster than below the table, which is actually
Yeah, there's
measurable.
someone has come up with a clock that's so accurate that it depends on where in the lab it sits, how fast it goes.
Right. And what elevation the lab is actually built at, and all of those things, which
Yeah.
is interesting, but it is measurable that something on your table, which is like your head, is actually aging faster than your feet. Um, from walking around or even sitting. But what that ends up saying when you extrapolate is, like Alpha Centauri, let's just say that star like off into the distance, that time is different than our time. So, if we have two people existing in both of those places, what's happening when they're interacting with the world is actually happening at different rates between those two places based off of how the time is. Now, let's just say we're using quantum entanglement and we're able to communicate instantly across these two distances. The messages may come back completely different. And, we could say like, oh, hey, please don't fire that laser. There's people there. And then by the time they get it, interpret it, it may have already happened, or it could be a completely different space of time. And what that made me realize is, let's just say an interstellar civilization happens. Once that civilization, once that colony ship goes off, it's essentially game over. Like there's no longer, those timelines have completely diverged. And, you find that space and you come back and it's, Interstellar definitely has it somewhat right. But I think that the time delta of even just what you're experiencing time and then being able to come back into this time space, well, one, would you even be able to perceive it? Like, are we, evolved in a way to be able to perceive time in a different means? And then being able to come back and forth between those different time spaces, or even, like I said, communicate with instant transmission, it may just fundamentally not work at all.
Yeah, I mean, I think that the thing to when I think about that, it's there is a real problem where it's like once we start to think relativistically, we don't have like a common time anymore. And like the idea of a common time, especially when time is curved, space time is curved, makes even less sense.
What do you mean by that, by the way?
we
Just to keep it level set for anybody.
space time is curved.
Yeah.
That is general relativity. And I actually heard a great analogy for this. So special relativity is this notion that, basically the speed of light has to stay the same. And it has to stay the same because of electromagnetics. Like electromagnetic theory, like comes up with a value of c, the speed of light, and it doesn't have any kind of correction for how you're moving or anything like that. So that was a real problem in the 19th century when Maxwell came up with his equations. It's like, great, yeah, we can see that electricity and magnetism creates light. So it's an amazing discovery, but then it like created this big problem that actually a lot of people were trying to solve. And they were trying to do it by link contraction and making mass. Basically, they had most of the ingredients, but just no one was bold enough to say, "Oh, you also have to put time into the equation." And that's what Einstein did, and that's how he came up with special relativity, which is great. And so it kind of resolved that, created a lot of problems for like, what does it mean, like a common time now, what are clocks, things like that. But what it essentially did is created like this idea that if you are in an inertial frame, you're moving along at a certain time, and another person's kind of moving along like this at a different angle, like a different speed, say, all their physics have to be the same. And so what special relativity does is comes up with a way to like come with a transform for all the Lorentz transform for all mathematics. It works for all mathematics, or at least mechanics, and it allows you to reconcile these things. So Einstein really immediately realized there's this problem, which is, what if you're not still? What if you're actually curved?
So let me say this. Let me put this a different way.
Accelerating.
So you have two people. One is heading towards Mars, another is heading towards Jupiter, and they're going straight lines. Special relativity.
Saying they're going at different speeds. Maybe they're both going to Mars, different speeds.
Okay, different speed. Okay, so they're both going to Mars, different speeds. How do you resolve the difference in delta in time between those two?
And how are they going, if they do start doing a bunch of like Faraday style experiments on electromagnetism, how are they going to come up with the same results, given that they're going at different speeds, which would indicate that the speed of light would be different, but we're saying it can't. And so how can you reconcile those things?
Okay, so you're both going somewhere, different speeds, different locations. How do you make sure that your experiments line up? Special relativity.
Mm-hmm.
General relativity is, well, I'm actually not going in a straight line and I'm not going the same speed. I'm varying. How do you...
I'm accelerating.
I'm accelerating. How do you square those two?
Yeah. So now your lines, one of your lines is straight like this. The other line is no longer straight. Accelerating, is curved. How do you deal with this? Well, you're imagining my fingers now are in a plane, like on a flat sheet of paper, say. Well, the way you deal with this is you curve the piece of paper until it's straight, and then these things line up. So the thing is, it's that curvature. You have to curve the underlying space to make this curved line look like a straight line. And if you can do that, then things line up. So, and it's mostly like if you're in free fall, on a planet, or if you're like standing on the surface of a planet, like how do you make those things, like how do you reconcile the space-time issue and that? And what you have to do then is you have to like break apart basically Euclidean space altogether, start from scratch, start with sets and move up to topologies and manifolds and like kind of all the stuff with differential geometry to build up to the point where you can actually have a curved space and talk about math on a curved space. And then you can build the metric for that curvature, and then you can make the math work out again with the Einstein equations. And so that's what general relativity is. And yeah, so
That's it. That's
forget exactly the question. They put me on that tangent, but this is what I've been learning about for a while. So it's something I'm really interested in.
Yeah, admittedly, I forgot how we got here too, but it's okay. I'm underslept. Usually, I would have remembered that. No, but that's a really succinct way that I don't think I've heard it put together in such a way. I've heard like the whole like bending of space, but it's moving the actual. it's hard to say space twice and using it, but it's saying you're trying to track these two objects. They're moving a certain way. How can you make them so that they're moving in a way in which that makes sense? Oh, you just actually form the actual reality of the two and where they are around in such a way that it makes it easier, which kind of goes back to the whole invention thing. Like that's definitely an invention. It's not reality. You're not discovering how to do that, but I guess it makes the reality easier.
In this case, the implication is that our space-time that we live in is not flat. It is curved. Another really interesting, I think interesting anecdote was that, Newton, when he came up with his flow-storm mechanics, he worked everything out and everything worked well if you were talking about 2 planets. But if you're talking about 3 planets, that's the 3-body problem. And it's like, it's more complicated. And he had some arguments for doing it, but Laplace wasn't happy with them. And so what he set out to do is come up with a way to deal with celestial mechanics by curving space. So instead of saying that these planets move around each other, gravity is not like a force that's like tugging at like these bodies to pull them around. Instead, it's a curvature of space. And like if you ever go to one of those science museums and like, they have that little thing, that like vortex where you put a coin in and it goes down like that. It's kind of the idea, is that, except for this would be a space so that coin would constantly, without the friction, of course, it would just keep going around at the same thing. Turns out you can't do it. It's impossible. And Laplace actually figured that out, some reason or other. But again, the problem was he wasn't bold enough. If he had of like put time into the equation, and also had a lot more mathematics that just wasn't available back then, but he had to done that, he could have actually made it work. And you can actually talk about Newtonian space-time being curved as well. But the thing is, it's space-time and not just space. You have to have time. It's really the time relative to the space that is being curved. And that's what, but that at the point you can talk about gravity being curved. And so Einstein's gravity is just that curved Newtonian gravity with an extra term that has to do with relativity,
Time.
basically.
Yeah.
The fact that, you can't exceed the speed of light.
Yeah, what how interesting is that? Just it's so interesting, like, if you look back at like the ancient, like the Vedas, and I know I brought this up to you before, but like the Vedas and Buddhistic thinking and all that kind of stuff, they talk about how important time is with everything and how it's non-existent. And when you start getting into like cosmic and celestial or an eternal, that it's all, I think they actually call it an unfolding. And that's essentially what you're saying, is that, because like what the concept I'm getting at, I don't remember what exactly it's called, some Sanskrit phrase, I'm sure, where it's essentially that everything is constantly in motion and changing, and even just holding in your space, the concept of time to them is like futile in a way. And what essentially you're describing is the actual fundamental part of where we are and where we are in relation to other things has to be constantly considered. How things are unfolding, which is essentially what time is. It's how is it unfolding? What's the rate of its unfolding? And what's the interplay with this and everything else, which also is probably has something to do with why the quantum or atomic world is plays by such different rules.
Yeah, unfortunately, you can't really talk about those things together. That's the big problem in physics these days. But yeah, they both relativity and quantum mechanics completely change the way we think about time, and both kind of get rid of this concept of absolute time, where in Newtonian mechanics, you can just think of there is a 3D space at a single point in time, and that's the whole universe at a single point in time. And then there is this whole other 3D space, which is the universe at, like some tiny fraction of time after that. And you can keep on going like that, building it up. And they're all kind of self-contained and work together. It's like you'd have to have some kind of concept of velocities in there and stuff like that. But still, it's like you can think about everything in a single point in time, but that you can't do that in relativity. Once, especially general relativity, once you get out of that, it's the thing is you can't even really talk about how fast two particles are moving relative to each other. You kind of need to be with one of those particles, and really kind of they have to meet. So it's you get consistency with relativity, but everything gets a lot harder to understand. It's kind of like sometimes it's even a little depressing just how like it breaks apart the universe. But it's the thing that makes things work, and lots of really beautiful stuff has come out of that.
Yeah, well, I heard something once, like somebody giving a talk, and it was, you can do field artillery with Newton. You need Einstein for GPS. It's like for precision stuff, you need Einstein. What makes it depressing with what it says about reality? What do you mean by that?
Well, I mean, it's just this notion that we kind of feel like we're all in it together, we're all in this like universe together at the same time, and I mean that's certainly true to like a very very fine approximation, but it at some point it breaks down to the point where it's like, I mean, it doesn't. You don't have to think about it. You don't have to like know much math or like think too deeply about this to think about like when you look up at a star at night and the light that you're seeing is maybe millions of years old, and you think about what you're seeing, and it's like, well, you're not seeing that star is not in my reality. That was like, I don't know, it's like some distant Earth, before humans, that when that light was actually there. But is it actually there? I mean, if I were to try to communicate with that star at all, it would, it wouldn't be in its million years in the past. It'd be a million years in the future when it actually received that. And so it's like that. It's just the speed of light. It's like we're just completely disconnected from that star in some ways, which is I don't know. It's just it kind of makes it feel like it's not here with us in this universe in some ways. But of course it is, and that's just the shape of our universe. It's the way it works.
Yeah. Well, yeah. It's in one perspective, it's not, and then in the other perspective of like, I think it's Sunyata, and it's like the Buddhistic idea of like, there's that's like the awakening. Oh yeah, it's like the awakening of when you wake up and realize that there is no void, but it's all just a void. So essentially, like the space between particles that create us is just matter and void. But then the space between me and you, like I'm outside Lake Michigan, you're in Chattanooga. It's there's a space between us, but actually there's no space between us because of the sum total of things that come, once you start extrapolating out and out and out and out and out, it's actually all one big thing. So yeah, the light coming to us is a million years old, but actually it's all part of the same cosmos of what is reality. So yeah, no, I totally get that. But then that's like the weird thing about quantum though, is that the light takes forever to get us, and that's like the cosmological constant, right? Is that there's no thing faster than the speed of light. But then what about this whole like entanglement thing, where you can play with the particle, be like, oh, I'm going to move you to the left, and then the entangled particles moving to the right, and you can do that with some type of consistency where it seems to break that law.
It seems to, and I think I don't actually understand this well enough, like Bell's inequality and kind of like all the things about non-locality of entanglement to really comment it. But my understanding is that you cannot send information via this entanglement, so that it doesn't actually break the speed of light. It's like it doesn't break causality in that way. But
That's
the
interesting.
thing is, I can't explain why, because it does seem like it would. And I mean, definitely, I mean, there's been experiments that show that like the wave function collapse can be triggered on one side, and then it happens on the other side faster than the speed of light could get to it to make it happen. So there's nothing there that's causing, like the disentanglement on one side is not causing the disentanglement on the other side in a causal relationship, but they are happening at the same time because they are kind of the same thing. And somehow you can't transfer information that way, but I'm not sure exactly how that works.
That's fascinating. Yeah, I know barely any, but we're talking about once we left jazz and music. I'm at the point of being barely able to comment on most of what we're talking about, so it's quite all right. But that's interesting. I had no idea about that. Because I hear stuff about, like the geopolitical scene of like quantum computers are going to make hacking so much easier, and quantum entanglement is going to make for communications with satellites and satellite arrays and precision munitions and all that kind of stuff. I've heard so much about that in the past, I don't know, 18 to 24 months. I have never actually looked into, I just taken it at full stop. Like, oh yeah, cool. I guess you can send information, or theoretically send information that way.
There's a lot of bunk in quantum right now. It's like,
yeah.
I mean, most of the people that are really into it or don't understand quantum mechanics at all. And there are people that are, and the people that do really well are generally making much more conservative statements, but still optimistic. So, I mean, the thing is, there's quantum networks which are happening, and I think a lot of people means quantum networks means that the information is traveling instantaneously, but all it's doing is saying that you entangle the particles in such a way that in order for anyone to eavesdrop on the communication, they'd have to disentangle them, which is immediately you can understand that on the other side. So basically, you can tell that your network has not been tampered with. Absolutely. Kind of one of these weird, like with security, it's really hard to get those type of guarantees. So it is pretty amazing, but at the same time, it's much less than I think most people think it is. It's totally possible to eavesdrop on it. The only thing is, like, if you do, you get detected immediately, and you can just stop sending.
That's interesting. Yeah, that makes a lot more sense, because I think there was something that the Chinese Space Agency did where they're testing out having their power grid controlled from space, doing exactly what you described. Now that makes a lot more sense to me now. So it's doing it in such a way that they can switch the codes or somehow change it.
Make it secure. Yeah,
exactly. Man, so what this whole thing is getting me to realize, or I mean, it kind of goes back to the beginning of his interstellar situation is not, or so interstellar civilization is not really possible, is that a lot of things that are dreamed up is conservatively unlikely.
I've been thinking about this interstellar problem because you brought it up a bit ago, and I think yes, it's true that what you say is that you can go out and seed a bunch of planets. It'll take centuries maybe to get there, and then you're going to have a bunch of civilizations that they all came from a same origin, but they're not going to be anything we can think about as a civilization, because a civilization, you really think of having kind of a common governance and a common culture and things like that. And if any of these cultures, hundreds of years out, like met each other, they'd probably just immediately go to war. They'd feel so alien from each other. So it's not like you can have that, but it doesn't feel like uh, a common culture. But the thing is, speed of light, absolute. And what we're talking about, it's a distance over time, right? C. And so we're talking about a huge distance, which means that, that fraction the communication becomes very, very slow. But the thing is, if you kind of increase the denominator, then you can start to think about society again. And what that means is you could have an interstellar society, but it would have to just be much slower than our human society. And if you think about and this gets a little bit into complexity theory, but it's like if you have like your molecular processes. So these are very small, but they happen very fast. And then you kind of have your cellular processes, which are, much, much bigger, like use, like huge numbers of molecules. But they happen, all the processes, the chemistry and stuff happens much slower. But the thing is, it still happens fast. If we were to be shrunk to that size and like look at it, it would just look like chaos. We wouldn't be able to make sense of anything that's going on because it's happening so fast. Like our neurotransmitters going out are happening like on a millisecond, like, like time frame. And then if you look at this conversation that we're having, we're talking about maybe like 50, 100 words per minute, something like that, so there's like, that's a kind of normal human interaction, like the amount of information we pass back and forth to each other. And we do this at the scale that we're at, which is much, much bigger than our cells, the neurons in our brains. But we have this kind of speed. And so like there are communication systems, which are now actually running more or less at the speed of light, are sufficient to have, the society that we have now. And, before, for a long time, it was really the speed of a horse was the speed of communication. And then you had to have like stops along the way to like make sure you could keep the horses going all the way to where you need to get. But that was fast enough to have like a Roman civilization. So, it doesn't have to be the speed of light. But the thing is, like, the speed of light is the limit. And I think we just have to kind of accept that. There's not like it would be completely new physics to come up with some way to get around that. But the thing is, you can imagine a society that's built out of something that's bigger than humans, or maybe very slow humans or something like that, where it would actually make sense to communicate that slowly, where the times, you're talking about like Alpha Centauri, I think that's a 1.5 light years, something like that. So, we'd only have to like scale things down by like 2 or 3 orders of magnitude before that becomes kind of the normal pace of communication. So, I don't know what like something like that would look like, but if you want to think about like, could there possibly be an intergalactic or interstellar civilization? I think the answer is yes. But I don't think humans could do it without like some kind of severe modification to what we are. And I think if there was a civilization out there that was like this, I'm not sure if we would even perceive it, because it would be so slow that we just wouldn't consider it to be like a dynamic process, and we would probably just ignore it.
That is a really interesting thought. So, yes, it would be like a much slower Pony Express. We're like, yeah, you can have it, but everything going from one side to the other would have to go through this stage. So it'd almost be like is probably influenced by the fact that I'm getting back into Lord of the Rings, but it's like the elves in Lord of the Rings, where they're just like, dude, our culture is pretty much what it is, and the divergences in it are, divergences that happened so long ago, and the scale in which we work at is so much larger. So it would have to be a very rigid, in a way, culture and society to be able to say, like, we're not going to come up with a new government before we hear back from whatever space. And
Yeah, there's this book, a Neil Stevenson book called Anthem, and it's a really good book. But you have to read pretty much the first 400 pages are all exposition and super boring. So you have to get kind of past that before the book is really, really good. But and most people don't make it that far. But it has this concept of this like monastic culture that almost I think everyone participates in. Everyone has to be a monk for a year, but then like a tenth of the population or some small percentage of it have to be a monk for 10 years. And then a very tiny percentage have to be a monk for 100 or it's not just they have to be a monk for their whole life, but the thing is they can only interact with society. Like the people in it for a year come back after a year. The people for 10 years only interact with the rest of society every 10 years. And then there's this other group that can only interact with 100 years, and maybe there's 1,000 years. I can't remember, but the idea is that each one of these levels, they're thinking about society and trying to make things better for society at different timescales. So there's like problems that you can only really think about if you're thinking about on 1,000-year timescales. And so, you can almost imagine having something like that, and it would be that very most remote monastic culture that would actually be what's keeping civilization alive for the rest of it, across the stars, because they would be able to communicate back and forth, every 1,000 years, and they would just like their whole lives would be committed towards, anticipating the answer or like coming up with good questions to ask or good things to tell other cultures to like keep the civilization alive. But they would, but the thing is, the rest of the culture, again, they'd be pretty much disconnected from monastic culture and wouldn't even really know about the civilization. I mean, they would every 1,000 years maybe they'd learn about it.
That's wild.
You should read it.
Yeah, that I might. That is. I'm going to look it up at the very. I'm going to put it on the queue if I end up getting to it. I don't know. Admittedly, but that's wild. Something I've been thinking a lot about, and I brought up in a different episode and a different conversation in this season that this is going to go out in, is like how to think in 1,000 years, like for 1,000-year time scale. Like that's something I've been actively trying to think about, because once you like, okay, climate change is real and the Earth is changing, but it's also changed a lot. And then if you look back like 13,000 years ago, the climate that changed then was horrific, and for like 1,000 years it was hell on Earth. But we went through it, and that's part of the onus of what I've been thinking about, because I've been thinking a lot about my kids, and like, okay, I woke up today and I went for a walk, and it was 6:00 in the morning and it was 50 degrees outside, and it's November 15th. Like that was never the case for my childhood, but it's gonna be the case for my kids for sure. It might end up being warmer, so I've been trying to think about things, and that was what sparked thinking about things for 1,000 years, and also thinking about, oak trees, and, like back when Europeans first came to North America, there would be 1,000-year-old oak trees everywhere. But now we don't have many of them because we chopped them all down for firewood, which is so heinous. Anyways, that's interesting though, because what you're essentially saying is, if we were to have an interstellar civilization, there would be a re-emerged class of shamans that would be communicating with the rest of the stars, and they'd have to be thinking about things at a much more galactic scale.
I'm just saying that's one way you could do it, possibly, but I'm not sure if anyone would be invested in that enough to make that happen.
There's enough Lord of the Rings nerds. I think it would be a distinct possibility. But we can end it here. This was awesome. Thank you for taking the time and coming on. Do you want to say
Yeah,
anything
it's
else
fun.
before we wrap? Or
No, I've been doing a lot of talking.
it was excellent. It was enthralling.
If you like what you're hearing, please follow the show on whatever platform you're hearing it through. And if you would, give us a rating as well, as both of those help keep the show going and get it found. One last thing. If you want to submit a topic for me to cover, throw me a person you want me to interview or talk with, even if you want to talk with me, or you just want to tell me how terrible of a job I did on something, check out bandwidth.productions to visit the site and drop us a note.